In this video, we're just going to do some more practice problems. If you're here, you should have already watched the previous one where we looked at the concepts for acceleration. And so you already know more about it. Let's just jump in and do some more practice problems. Here's some stuff on acceleration. Good luck. Hey there, welcome back. Got some more problems for you. We're going to continue looking at acceleration, but we're going to look particularly at displacement and acceleration. In a previous lesson and video, just talked about acceleration from the concept of what's happening with the change in velocity and the fact that you could have a change in direction, and that will also affect an object's acceleration. But nowhere in that previous lesson or what we talked about did we mention anything with the actual position of the object. It could be you, for instance. So put yourself in that position. And I recommend that when you do a lot of these problems, pretend you are in the situation that is there. It doesn't matter if you're talking about someone moving down a hill or running here or there, whatever, or a ball rolling on something. If you imagine that it's you doing that, because we're familiar with how things feel when we speed up and slow down and turn, it really helps sort of, I think, compartmentalize the conditions for what we're looking at so that it makes some sense when we look at the variables. Why are we writing this here? Why are we writing that variable there? Okay. So with that, let's just take a look at what we've got. So let's graphically analyze two scenarios with an object exhibiting positive velocity. All right. So that means we're going to need a graph. All right, so we've got, I always go back to the blue. So we'll have a graph here, and we're going to need two situations. So let's just go ahead and draw our two graphs. All right, so we've got a situation where we want to look at a positive velocity. So we have to have a positive, let me put that positive symbol on the other side. We need a positive velocity here, and we need a positive velocity here. All right. So if we think about this for a second, it kind of makes sense. It doesn't matter which one you start on. It kind of makes sense that if you have a slope line like this, that we could look at that slope line, and obviously if we're looking at delta V over delta T on both of these, right? Let me put that back. That's better. If we have delta V over delta T, then what we just drew on the right hand side here, that the acceleration on that, well, that's definitely a positive slope, positive velocity. So that condition fits. Whatever the numbers are, it doesn't matter, right? So now we come over here, and what we need is positive velocity. Now, if we were to draw over here something like this, well, that would be a negative velocity. That doesn't fit this condition, so we definitely wouldn't show something that looks like it has a negative correlation to it, right? We would not draw that. So there's really only one other situation that fits. If we draw a flat line, then what we have is an acceleration that equals 0. It's moving at a constant velocity, and it's not changing direction, and it's not speeding up, and it's not slowing down. It just continues to move forward in a forward direction, which involves positive velocity. So those two situations, that's basically it. All right, no numbers needed. But now we're going to look at we're going to take this concept and merge them together a little bit here. So let's derive the equation for the displacement of an object, because nowhere in any of this do we have displacement anywhere. But if an object is accelerating, then obviously it's changing its position. But nowhere in here do we have anything at all with displacement. So we need to get displacement in here. We need to get delta x, because we're still dealing horizontally, right? So we need to get delta x into this equation. Let's go to the next slide. We're moving at a constant acceleration, right? Moving at a constant acceleration. I'm going to go back to that. I think I'm going to like a slightly thicker tip on that one. So we've got a constant acceleration. So let's think about this for a second. If we have an average velocity, then if you're moving at an average velocity, it kind of makes sense that the velocity is kind of staying the same. But no matter what, whenever you measure some sort of rate of change, at a minimum we look at 2 points, right? We know that when we look at our slope-intercept form or equations, we basically look at 2 points at a minimum to get that slope line. We usually need more than 2 points to get a really good slope line. But if we're assuming that it's constant, we're going to just use an initial and a final, draw a slope line, right? So that means that we've got our initial plus our final, and we would divide those by 2, right? Because of 2 points, we would divide it by 2, right? So then we have something else we need to think about here. We've got this, and when we look at velocity, when we first talked about velocity, we did talk about displacement. And we said that the change in the position, the displacement over time, we have this equation here. We have v equals d over t. So when we're talking about speed, it's just v equals d over t. When we're talking about something with direction, we tend to use displacement, and we've already said that we tend to use x or y for our displacement. So we have these two equations here. So now we ask ourselves, well, what can I do with this? Well, we have two things that are the same. So let's set them equal to each other. All right? So we've got the average velocity. It equals, right? We know that average velocity equals delta x over delta t, and then it also equals our initial plus our final. Since it's just 2 points, we're just going to divide by 2, right? So now that we have that, now that that is there, we can just basically take that, get rid of it, and bring these two sides in line with each other, correct? Correct. So now that means we've got delta x over delta t equals the initial plus the final divided by 2. All right. Let me, I'm just going to lasso this stuff, kind of make it a little bit smaller, give myself plenty of room here. All right. Now at this point, what we basically have to do is just do some math so that we want displacement basically by itself. What's the displacement with constant acceleration? If we need to get x by itself, that means we need to multiply this side by delta t, so we need to multiply this side by delta t. That'll cancel out there, so we've got our displacement equals vi plus vf divided by 2, and then times delta t. And so this part right here, vi plus vf over 2, that is really like 1/2, right? Times our initial plus our final times delta t. And then that is our displacement. And so you'll notice on your equation reference sheet that I gave you, that's one of your equations that is there. So if you have constant acceleration, you can, all you need to know is your initial, your final velocity, and your time. You just have to somehow find those three variables. You do that, you can solve for the displacement. All right. Let's do a problem with this. Let's see what we get. All right. It's Maggie this time. I think before it's been Carlin. We've had all kind of neat names. I'm going to come up with all kind of good names there and stuff. So, constant acceleration and displacement. Maggie applies brakes to the car. It slows uniformly. Uniformly lets you know that it's at a steady rate. That's what uniformly means in this situation. Pretty much any situation where the word uniformly, it's referring to kind of a constant, steady rate of some sort of change. All right. It slows uniformly from, that should be from, not form. It's a typo. Sorry about that. From 15 meters per second to 0 meters per second in 2.5 seconds. All right. So delta t we've got is 2.50 seconds. And then from 15 meters per second to 0 meters per second. So it looks like the final would be 0.0 meters per second, and it looks like the initial was the 15 meters per second. So how far away from the stop sign does she need to be when she presses on the brakes? Well, that's a displacement, because if the stop sign is here, what x equals how far she needs to be away from the sign. Hit those brakes so she doesn't, so she stops right at the stop sign. That's that 0 mark right there. So we've got all our variables. So with all these equations that we're going to see in physics, essentially what you want to do first is list out what you've got, find what variables are you're solving for, what you have. Find an equation that already fits that condition, because all these equations are on the reference sheet anyway. And then if there's only that one missing and you've got all of these, just plug and chug that one particular equation that you've got, right? And so we already had that delta x equals 1/2 vi plus vf times delta t, right? So we've got 1/2. Our initial is the 15 meters per second, right? Plus the final, which come to a complete stop, so that has to be 0. And we tend to write 0.0. You do include that. Don't just write 0. Remember, it's a measured value, so there's a decimal to give significance to the measurement, right? And then that's times time, which we see is 2.50 seconds. Okay, so now that means we've got half of 15, so that gives us what, 7.50 meters per second times 2.50 seconds. We should be able to see that the seconds cancel out, right? Seconds units cancel out, so we're only left with meters. This is a good thing here, right? So we've got 7.5 times 2.5. That gives us 18.75 meters, right? And so we look, we see 2.50 seconds, 15.0. We're dealing with approximately 3 significant digits. This is an exact answer, 18.75. So if we were looking at sig figs, we might say approximately 18.8 meters, right? We might say 18.8 meters. 18.75 is very precise. So all that means is you could go back here, put a 0 there, put a 0 there. Remember, you add in those zeros, it doesn't change the value of it, it just gives you more numbers to work with. So 18.75, it's a really good answer. If we were to stick with the sig figs, then we would just use that. Right? I hope that helped. Keep working on those practice problems. Ask questions as always. So it's good to see you. Take care. I'll see you in another episode. Bye. And there you go. Plug and chug. In this particular example, it was just applying what we had learned in another lesson. When you're trying to find displacement, sometimes with what you can't directly measure the displacement because you're just observing the object in motion elsewhere. But if you have a way of measuring time, you have a way of measuring velocity, then understanding that, or we just assume that if everything is under a constant condition, that we can just plug and chug into that. We can merge those equations together, and we've got this derived equation for displacement with constant acceleration. We'll look at others as well. There's a whole slew of them. We'll look at those in some other videos. I just thought this would be a little helpful for you, help out with some of your practice problems. Good talking to you again, and I will see you soon.